Welcome to qnawire.
Okay, so I've drawn out our problem here. We've got the spring constant over here, 500 newtons per meter. And our block over here is it's a 5 kilogram block, and it's going at 6 meters per second. And basically, if we want to know the maximum amount this spring can compress, it's basically just a conservation of energy problem, right? So the kinetic energy of the block, when it's zooming along, is going to be equal to, whoa, that's a bad equal sign. There we go, equal to the potential energy of the spring when it's compressed. So we know the equations of both of those. The kinetic energy is 1/2 mv squared. Potential energy of the spring is 1/2 kx squared. Excellent. First thing we do is get rid of the 1/2s. We can see structurally that we don't need them in the equation. Excellent. Now, when we want to first, okay, so the A part, we want to find the value that the spring compresses by, and that's x. And in the B part, we want to know the velocity of the block, assuming that we know how much it compresses the spring. So we're actually going to reuse this equation here. You can just kind of remember this. It's a good one, and kind of know how to get there. But we're going to reuse that twice. So the first time, we're going to use it for figuring out how much the spring compresses by. And so solving for x, we get x is equal to, so this x is equal to the square root of mv squared over k, and that's 0.6 meters. So that means that when this box, this 5 kilogram box, is zooming along with that amount of kinetic energy, that's how far it can compress the spring. Great. So now we're going to assume that the spring, for part B, we're going to assume that the spring compresses a distance of 0.15 meters. So, I ran out of room up there. Okay, I'm going to write the 0.15 down below that little sign there. So 0.15 meters. And that's going to be equal to x for part B. Right. So for part B, this time we're going to isolate the velocity that has to be going with in order to compress it by that much. So let's do that now. So we take the same equation we had from before, and instead of solving it for x, now we solve it for v. And we get that equal to square root of kx squared over m. And we sub in the values that we know, remembering that this time x is equal to 0.15 meters, and we get that the velocity has to be 1.5 meters per second. That's how much it takes. That's how much energy the block has to have in order to compress the spring by that far. One thing that I find really interesting about this problem is that we have used conservation of energy, but we've never explicitly calculated how much energy the box has or the spring has at any given compression. We just started out with the assumption of conservation of energy, and then we just equated those, and we were able to bypass this step, which I think is cool.